Okay, welcome. So the lecture I'm going to be giving today is going to be the last topic we're going to cover in mechanics. This is going to be impulse and momentum. So what we're going to do from here, I should share my screen first before I start talking too much. And there we go. Okay, so basically what we're going to do is we're going to show how this is some of the definitions we're going to use for momentum are a consequence of a combination of Newton's second law and another one of our kinematics equations. So really, just like the work energy theorem, this is gonna boil down to that. Now, similar to with the work energy theorem, what this means is it has implications for when your net force is zero. And we'll get to that in the next lecture. But for this one, we're gonna be starting with those two ideas. Okay. So as a reminder, what we have here is we have the second law, and this was F net sum of the forces equals mass times acceleration. Now the kinematics equation we're going to use. There were a bunch, but we're going to use another one of the ones with acceleration. And this time we're going to use this V final equals A delta T plus V initial. Now I'm going to rearrange this just a little bit. So you have V final minus V initial. That was just delta V as a reminder. I'm trying to maintain consistency equals A delta T. So that was basically the definition of acceleration. Delta V over delta T equals acceleration. That's basically what we're saying here, if acceleration is constant. Now, we can solve second law for acceleration. So we can say, just like last time, that F net over M is equal to A. And then we can do this substitution into there. And we get V final minus V initial equals F net over M delta T. Now, typically what happens is you bring the mass over to the other side. So you would get MV final minus MV initial equals F net delta T. Okay. And this is basically the equation that we're going to be dealing with. Now, just like with kinetic energy, what we saw last time is like what we have here is we have a change in some quantity. Okay. So what we're going to do is we're going to define both sides of this equation. Now, the first one I'm going to define is actually the one that's less commonly used, though it is common, is impulse. And impulse is the right side of this equation that I gave here. Sometimes it's done with the symbol I, sometimes it's done with the symbol J. Both of those things have other meanings in physics, so a lot of times you won't even give it a symbol. You'll just know that this quantity F delta T is in fact an impulse. Hold on here. I am curious what our book uses. I don't remember. It doesn't look like they do use yeah, it looks like they just use fnet. Yeah, fnet delta T. So again, sometimes you'll see it as I, but really it's just F net delta T. This would be net impulse. So this will be the combined impulse from all forces. And then just any F delta T, this is the impulse from a particular force. Okay. And the units from a particular force. The units of impulse are in just Newton seconds. So you can also break this down. As a reminder, a Newton is, put this in brackets so we know their units. That is a kilogram meter per second squared. So an alternative unit for impulse would be kilogram meters seconds per second squared, and then you can cancel one of the seconds. So the units are also kilogram meters per second. Now it turns out that this is what we tend to use for the other side of the equation, the MV side of the equation. But for impulse, that tends to be given in Newton seconds. Okay. And basically what it is, it's sort of a quantification of how much force has been applied in terms of time. All right. So, the idea is that there's something fundamentally different about applying a particular force for a split second versus applying it for an hour. You're going to have vastly different effects. And so basically that's what impulse is trying to do. It's trying to sort of group the relevant things that could affect how an object changes its motion, namely the force and the time over which it's applied. Okay, so that's the idea behind this. All right, so this would be that's what impulse is. Okay. Now this is similar to work, and work was force applied over a distance. Force applied over a distance. Impulse is a force applied over a particular unit of time. And it's not that they are unrelated. Like for any given force, it will do some amount of work. That amount could be zero. But it will also have some impulse. Okay. So they're not separate phenomenon. It's not like you apply either one or the other. Whenever you exert a force, you do end up applying both. But it's a different perspective. It's a different way to look at the force and the effect that the force has. Okay. So hopefully that sort of makes the distinction clear about what impulse is. Now, the other side, you possibly recognize this. The other side is momentum. The other side of that equation was momentum. Okay. And momentum is just simply given as just mass times velocity. And momentum is in fact a vector. Now what this means is it means impulse is also a vector. So I'll just note this. This is a vector, and I should probably indicate this in vector form. It's in the same direction as the force. Okay. So what this means for our purposes is that when we were dealing with work, the direction was not often relevant. Like it might be somewhat relevant in making sure that our force was going in the same direction as our distance, but once we'd established that and gotten the correct component of the force, direction ceased to be an issue. Direction was not an issue with kinetic energy. Kinetic energy was a scalar. Momentum will have a direction. Okay, same direction as the velocity, just basically the velocity weighted by the mass. Now, when Isaac Newton wrote the Principia, he called this, I don't think he had the term momentum. What he called it was the quantity of motion of an object. And basically what he was doing is he was saying, when you have an object that is moving, the way in which it will impact other objects, stationary or moving, is dependent not only how fast it's going, but how much mass it has. Okay. So this was basically how he quantified motion, was that it had some amount of mass and it had some velocity. Okay. And that was basically a quantity of motion. Now we call this momentum, but it is fundamentally the same thing that he was talking about. Okay. And again, it's just mass times velocity, same direction as the velocity. All right. And same direction as the impulse. Because what we have here, if we go back to that original equation, is, oh, by the way, the units, it's just mass for kilograms and then meters per second for velocity. So that's just kilograms meters per second, which was exactly what impulse reduced to when we canceled its newtons out. So again, when you're talking about momentum, you tend to measure that in kilogram meters per second. And this is one case where we don't give a special unit to this new quantity. Like we don't have a special unit of momentum. We just say kilogram meters per second. So that's what we're talking about there. All right. Now, going back to that equation, what we had here is we had F net, and I'll put it in vector form, worth doing. Delta T equals MV final minus MV initial. Okay, so what this was impulse over here. And those should have vectors as well. And then what you have is you had your final momentum minus your initial momentum. Okay. And what this is saying is that impulse is equal to delta P. When you have something final minus something initial, that is just the change in that thing. So impulse is equal to change in momentum. Okay. So this is the key, and I should include that it is the net impulse because it was F net. Is that a net impulse on an object causes a change in momentum. Now, it turns out that this formulation is also an alternative way of writing the Newton's second law. So the second law, as we have been discussing, is written like this. It's written as F net equals MA. But the way you can end up doing this is you can basically end up doing it with and if you're in non-constant acceleration, it's a little different. But what you can end up doing is you can end up rewriting this just a little bit and saying, okay, this is M delta V over delta T. And then that would be the M delta V just becomes delta P over delta T. So this is the idea that what a net force causes a change in momentum. Now, this is interesting because it has certain implications. That if you can change your momentum in any way, this implies that you can actually exert a net force on an object. And this is something that's true. Okay. So an example of this would be like if you were is this well, okay, let's say you're just out in microgravity, you're in orbit. And you don't have anything to push off of, so you're basically just stuck. You're flailing, you can't move yourself. But if you have like a backpack that you can take off, what you can do is you can take that backpack and throw it in the opposite direction that you want to go. And basically, the net result of this is it is a net force because you changed your own momentum. Okay. And the idea is you can also think about that in terms of the force. You pushed off the backpack. So when you pushed off the backpack pushed back on you. So that's another that you can think about it in terms of third law. But another perspective is that you basically change your momentum by effectively reducing your mass and sending part of that mass with its own momentum off in the other direction. Okay, so this is another perspective on this rule. So this is the main thing that we're going to be using when combining impulse and momentum. Impulse causes a change in momentum. Net impulse is equal to the change in momentum. Okay, so I wanted to do a couple of examples in this. So the first one I'm just going to grab is the first example from the textbook, and I will get there eventually, maybe. All right, so that's tiny. It's big now. All right, so this one says, calculate the momentum of a 2,000 kilogram elephant charging a hunter at a speed of 7.5 meters per second. So this one is really not too bad. All you need to do is you just need to do momentum of the elephant is equal to m mass of the elephant, velocity of the elephant. So 2,000 kilograms times 7.5. This would basically be 15 and then 3 zeros. So 15,000 kilogram meters per second. Okay. And then for part B, it's compare the momentum with a tranquilizer dart. So momentum of the dart equals mass of the dart, velocity of the dart. It's equal to 0.04 times 600. And that is just going to end up giving you 24 kilogram meters per second. So that dart doesn't anywhere near get the amount of momentum that the elephant has. Its kinetic energy is probably closer, but not nearly the amount of momentum. Okay. So C is the momentum of the hunter, which would just be the mass of the hunter times the velocity of the hunter, which would be 90 times 7.4 times 7.4. That would be 9 times 74, which would be 630 plus 36, which is 666 kilogram meters per second. So also quite tiny. Okay. So that is basically how you would approach this one. All right. So whenever I'm recording, I'm always neurotic about doing my mental math. So I'm just going to check it. Times 7.4. And yes, I'm right. 666. Okay. So that would be how you would do that one. All right. So that one was just, basically straight calculating momentum. I'm going to grab another one now. I don't remember which number this was. So I'll put it up and, you can go find it if you want. Says a professional boxer hits his opponent with a 1,000 Newton horizontal blow that lasts for 0.15 seconds. Calculate the impulse of the blow. Oh, it's a little too much there. Calculate the impulse imparted by this blow. Okay, so I'm gonna you will see me oftentimes use the symbol J for impulse. I don't like I because I is I think of current, but we don't really use current in this context anyway, so you could use I if you were so inclined. So it would be the force times delta T. And it's not a net, it's just from the blow. So it would be 1,000 newtons times 0.150, which would be 150 Newton seconds of impulse. Okay. What is the opponent's final velocity if his mass is 105 kilograms and he is motionless in midair when struck near his center of mass? Okay, so basically what we would do, that would be part A. For part B, we would say, okay, J is equal to his delta P. Now, for his initial P, we know that I'll just say his mass was 105 kilograms, but his initial velocity was 0. We know that 0 meters per second. We know that because it said he's motionless. So his initial momentum is just 0 kilogram meters per second. Now his final velocity is what we're looking for. Okay. His final velocity is what we're looking for. Now we're not going to be able to get that directly. We're going to have to find the final momentum. Okay. So delta P is just going to be equal to P final minus P initial, which was 0. So that's just equal to P final. All right. So we have our J is equal to P final, which means that 150 Newton seconds, and remember, that's the same thing as kilogram meters per second, is equal to P final. And now all we need to do is we can just say, okay, this is equal to MV final. And that's, 150 equals 105 V final. And then dividing both sides by 105, we will get V final is, and it's going to be a little bit less than 3/2, or 1.5. It's 1.43. 1.43 meters per second. Okay. So yeah, it moves him a bit, but it's nothing huge, nothing terrible. Now, similar part C is similar in that we still want to use J is equal to delta P, but this time it's going to be hitting his head. So the main thing that changes is now the head is free to pivot. So his entire body's not going to move, but it's just his head that's going to move, okay? And the head won't, the neck will eventually stop the head from moving, but basically it's the head is it's gonna be the head's momentum that changes basically. So this time, instead of 105, our mass is 10. And our V initial was still 0. Our V final is what we're looking for. Our P initial is still just 0. Our P final, it's basically our impulse hasn't changed. So we can still basically just say, okay, our P final is going to be 150. And from there, we can just say, okay, 150 equals mv final. And when we solve for this new m, with this 10 kilograms, we get our velocity is equal to 15 meters per second. Now, that is like 10 times as high. Okay, it's a bit more than 10 times as high. Now, as a reminder, doubling doesn't quite work, but it's not a bad rule of thumb to check this out if you want to think about it in 30 miles an hour. So basically, this is that your head goes from motionless to 30 miles an hour. Now, you get in a crash at 30 miles an hour, that's not nothing, but if you're going that, if it's happening that quickly, then you're getting things are rattling around and they're pretty good. And for those of you that are familiar with boxing, this is one of the things that's come up in boxing, as older boxers are retired, is that you can take your head can be okay with a few of these blows, but if you take a bunch of these and your brain is constantly doing this inside of your head, that can really start to do some damage to your brain. So this is just one sort of thing to consider when looking at that. I did want to do one more, just to bring in the directional aspect. Now, I'm not going to do much with the directional aspect of momentum. I will be very honest with you. The directional aspects are some of the hardest things in momentum. They require a lot of practice, and you would spend a lot of time practicing this. We'd have more time devoted to this in a full mechanics class. I'm not going to do that because like I say, the math just kind of gets nasty. But I do want to show you this one just so you can see kind of what goes on here. So basically what we have here is we have a ball. I'll draw the picture. And we have the horizontal, so we'll have the ground here. And we've got the little kid throwing it. And what he's doing is he's launching this ball. And we know it won't actually be on a straight line, but we'll draw it like it's a straight line, just so we can have this. And I didn't quite draw that enough. It should be steeper, but whatever. So that is 60 degrees. It's 60 degrees above the horizontal. Okay. And then when it bounces, it says it's now 60 degrees above the negative x direction. Okay. So one of the things we can do here is we need to appreciate that momentum is a vector. So it will have an x component and a y component. So let's do that. Okay. So I'll do the initial first of all. And the x component would be in terms of m, so we don't know, it would just be m, and then it would be the x component of the velocity. So it'd be m v sub x, and this would be m v sub y. Now, if it's 60 degrees, the x component would be a cosine, which a cosine, that would be the short side. So this would be just it would be so it'd be m cosine 60 times v. Okay. And then this would be m sine 60 times v. And this would end up being mv over 2. And this one would end up being square root 3 mv over 2. Okay, so that's basically what we have there. Now, again, this figure is not drawn quite correctly. Now, the final momentum is basically you're gonna have P sub X final and P sub Y final. Now, with P sub X, the main thing you need to appreciate is that it's going in the negative direction now. Okay, that's very important. So this time it's going to be negative mv sub x, which would be negative mv, and it's still the cosine of 60. Cosine 60 degrees, and it says the same speed, so it's still just v, and this would be negative mv over 2. Okay. And then the y and the y actually doesn't change because it's still going up. So and it's still just so it's still positive, still in the positive direction. So just m v sub y, which would be m sine 60 of v. And because we still got the same angle and y is still going up, so this would still just be square root of 3 mv over 2. Okay. Now, if we wanted to find the impulse, again, the impulse is going to be equal to the delta P. Okay. So we need to find the delta P. And we need to do this vectorially. So delta P, this is going to be P final minus P initial. Now, as a reminder, what we do is we do this in components. Okay. So what we do is we'd have, okay, this is going to be px final minus px initial. And then that would be, for those that are familiar with this format, in the I hat direction, in the x direction. And then plus py final minus py initial in the j hat or x or y direction. Now, it turns out that py final, that should have been an F right there, equals py initial. So when you subtract them, this thing just goes to 0. So the only thing we have here is we have the x that's relevant. So it would be negative mv over 2. That would be the final minus mv over 2. And when we solve this, we just get negative mv. Okay, so that is our change in momentum. It is negative mv. Now, what does this mean? What does the fact that it's negative mean? Well, it's the fact that it's negative, so we could say that our impulse right there is negative mv, or, plugging in the v, j would be negative 10m. Either way. What this means is it means that remember, the impulse is in the same direction of the force. It means that the force was directed to the left. So when you think about what the ball is doing, what force is experiencing from the wall, it's a big force to the left, right? It's when the ball hits the wall, the impulse is it basically, the wall won't move. So as a consequence, it exerts a large force on the ball that forces the ball to very quickly accelerate and go back the other way, is basically what's going on. So that's what the negative is saying. It's saying that, okay, we're going in the negative direction for this one. All right. So those are a few examples that I think will help you with the next homework, not this week's homework, but next week's homework. So I'm going to go ahead and end things there, but hopefully this will be clear. All right. Thank you for joining me. I'll see you next time.